taking Charlotte's information and how do we put it onto practical farms and increase integrated pest management. I'm also going to take the opportunity to introduce the Achieving Sustainable Agricultural Systems project, which is funding a lot of this work. Okay, I'll use the mic. Okay, can you hear that better? Yeah, good, okay. So I just firstly like to introduce Centre for Ecology and Hydrology, because you probably don't know who we are. So we're an independent, not-for-profit research organisation. We're part of the UK Research Councils, which is in itself part of the Department of Business, Innovation, Energy and Industrial Strategy, BEIS. 450 staff, 4 sites across the country. We specialise in long-term experiments and monitoring of agricultural systems. Track record, in the 1960s, we were the organisation, our predecessor organisation linked the use of organochlorine pesticides, DDT, to eggshell thinning in peregrine falcons. 1980s, we identified the loss of hedgerows and wildflowers in the countryside. And 1990s, we worked with DEFRA, Natural England, on the agri-environment schemes to help put these habitats back. 2000s, led the farm-scale evaluations of GM herbicide-tolerant crops, and most recently, we led the study across Europe on neonicotinoid pesticide impacts on pollinators. So, long track record of working on agricultural systems. So, the ASSIST programme, Achieving Sustainable Agricultural Systems, it's a 5-year, £11 million research programme. It unites the expertise of my research council, the Natural Environmental Research Council, with the Biotech and Biological Research Councils, with full support from the farming industry, which is absolutely critical. The aim is to develop new ecologically based sustainable agricultural systems, which we hope will be more efficient and resilient to future environmental shocks. And then at the same time, we recognise that if these are going to be successful, we've got to integrate these with modern systems of precision agriculture. So that's the sort of background. The programme involves Centre for Ecology and Hydrology, that's us at Wallingford, Rothamsted Research and the British Geological Survey. The first thing we did with ASSIST was we held a large stakeholder workshop, and we issued a questionnaire, and maybe some of you filled this in, to over 100 participants. And the aim of this was to help us identify what the future challenges are for agriculture, most importantly to actually share innovation. So conferences like this are incredibly useful, and we use the questionnaire and workshop approach to gain that sort of knowledge, and then take the first 2 things and actually co-design practical solutions to some of these challenges, and ultimately to influence government policy regarding sustainable agriculture. So that was the sort of key aims of the workshops. Now, this is a short list of challenges facing agriculture. I admit this could be as long as a Leonard Cohen record if you wanted it to be. And so we've simplified it, and we're just basically focusing on degraded soils, which came out very strongly from the consultation, growing pesticide resistance, fewer active ingredients, and then there was also more concern around extreme climatic events. So the importance of improved integrated pest management, what I'm going to talk about today, came out very, very strongly from the consultation, as did some of the solutions that were co-designed from those workshops. So very broadly, in terms of the solution that the industry sort of came up with our help, was the idea of ecologically based agricultural systems, a systems approach. And you can reorder the words, but you get the sense of where we're coming from. It's about the optimum management and enhancement of the underlying ecological processes that support food production, crop production, to improve efficiency and sustainability of agriculture, and ultimately going to make it, hopefully, more resilient to future shocks, perturbations. So it's a systems approach. And then, again, very much integrated with the best of precision agriculture to maximise efficiency, minimise the environmental risks. So this is an integration as well. So what evidence do we have about how we could go about maximising IPM from CEH research? So the first piece of evidence we had was that the ASSIST project has a number of PhD students. One of those PhD students did a meta-analysis of all of the studies they could find on natural pest control systems in agriculture across the globe, and he published it very recently in Ecological Applications. And what he found was that where management enhances the diversity of what we call predator functional traits or characteristics, you get maximum natural pest control. What we mean by functional traits or functional characteristics are the greatest diversity of hunting strategies. So you have ground-based predators, aerial predators mixed up. So it's not just about abundance, it's about the greater diversity of different strategies for your natural enemies. Similarly, things like pest preference, so some feed on slugs, some feed on aphids, the size of the predators, and their habitat preferences as well, whether they live at the field edge or in the field centre. But it's about that diversity of functional characteristics is the key thing to maximum integrated pest management. Second piece of evidence, it's very straightforward really. We did a study of 4 commercial farms where we compared the numbers of natural enemies we found in flower-rich margins compared to typical grass margins, and I'm sure you know this, basically sowing flowers increases the abundance and diversity of these beneficials, as well as pollinators as well. It's very obvious. Sow flowers, you get beneficials, and it was clearly shown from this study published in Agriculture, Ecosystems and Environment a couple of years ago. Third piece of evidence, which is the key really to ASSIST, is this spillover of beneficials into the crops. So we've increased the numbers by sowing flowers, that's great. But what we did on those 4 farms was we introduced aphid populations onto the wheat with the farmers' full support and knowledge. We didn't do it without telling them. And then what we did was we looked at how long those aphid populations lasted at different distances from the flower margin and the grass margin. And the graph on the bottom left-hand side, the axis is the number of days the aphid colony survived before it disappeared. And what we found was that the flower-rich margins, the blue bars, the aphid colonies lived the shortest period of time, therefore natural pest control was more effective compared to the grass margins, the red bars. But the key thing is that the aphid colonies lived the shortest length of time close to the margin. They lived a lot longer further away, 50 metres. So we found that basically the spillover of natural pest control declined after 50 metres into the field. So that was a spatial issue, a problem that we needed to solve. Similarly, we did some work on wild crop pollinators and found that wild pollinators do not venture right into the centre of large arable fields, so we have a similar problem with pollinators. So spillover is an issue. Third and final piece of evidence, we work on a large 1,000 hectare commercial farm near Buckinghamshire, the Hillsden Farm platform. And what we did was we removed between 3 and 5% of low-yielding land from cropping, created habitats for beneficials, pollinators, and natural enemies of pests. We found it increased the abundance very dramatically and diversity of these beneficials. And the key point with this project was that we found over 6 years that the yield of some crops was increased by as much as 35% when you take into account of the land removed from production, the 3 and 8%. For other crops that were not insect pollinated, for example, there was no net loss when you took that 8% out. We published this in the Proceedings of the Royal Society 3 years ago, and it's been very highly cited. It's some of the first evidence of this ecological agriculture and on a commercial farming system. So in terms of ASSIST, what we did was we took all this evidence and we worked with the wildlife farming company, Marek Nowakovsky, who'll be on the panel later, to come up with the design of the ideal habitats for beneficials. And this was based on all of that evidence you've just seen, plus experience from things like the Buzz project, which was undertaken a number of years ago. And the key principles of the design were we went for a perennial rather than annual habitat for our beneficials, because it was easier to control weeds like blackgrass, easier to maintain. Mixture composition was very important, not bog standard wildflowers. We picked them to benefit the natural enemies of crop pests and the pollinators. So we went for open flower structures for the parasitic wasps and the hoverflies, certain pollen or certain flower types to provide pollen nutrition for these species. Also, they needed to be robust and able to survive in arable systems. They needed to provide habitat structure so that certain species of predator could overwinter in these habitats. Needed to be reasonably cost effective and available from seed houses and reliable. And then the other point I would make is, and the thing that we mustn't forget, is that this is also about how we work together to increase natural pest control across whole landscapes. If we just work on individual fields and farms, we'll probably end up with a honeypot effect where we're just dragging beneficials from one site to another rather than increasing their population size. That's a very important point that we need to address. In terms of improving soil health, the co-design with the farming industry came up with a couple of solutions, which I'm sure you'll be aware of. It was about understanding and quantifying, measuring the benefits of practical soil enhancement approaches, cover cropping being the obvious one, but also additions of compost, organic matter, which a lot of farmers are doing, but no one has the numbers on those. And also developing and looking at intercropping systems within agriculture, which Assist is beginning to look at as well. And then understanding, using advanced techniques such as DNA barcoding to understand what the actual impacts are on the soil microbes, what's happening to the soil function. So that came out very strongly. So the Assist experiment, the multi-farm experiment we're undertaking, is on a network of 20 commercial study farms across the UK, provided free of charge by industry. This is the partnership working very effectively. It's what we believe, because we're working on commercial farms, it's an acid test of this ecological agriculture together with new agri-tech systems. So if it's going to work, it needs to work on these commercial farms. 20 farms means it's statistically powerful, so we can have some certainty in the results. It's a great opportunity for technology transfer and for complementary research. We have 6 PhD students working on these farms. There is also a similar experiment going on in grassland systems as well. The aim of the experiment, to improve soil health and structure by looking at the effects of green waste, compost and cover cropping, improving IPM, so looking at how flower-rich field margins improve IPM, the targeted species that we chose, how do they perform for a whole range of different predator groups, and then also how we move the beneficials from the field edges into the centre of the field, so overcoming that spillover problem. So what we're looking at here is sowing strips of wildflowers within arable fields to provide these pathways of benefits into the crops. So that's the critical thing, and that's where the new precision agricultural systems come into effect. So the experiment on each farm comprises 3 fields. The first field is business as usual, no treatments. We compare everything to this control treatment. Second field is what we term supporting beneficials, where we just have the special beneficial seed mixture at the edge of the field, which is very typical under agri-environment schemes. And we also grow cover crops 2 years in 5 with the spring cropping. So a fairly almost standard practice. The third field is the research treatment, where we're aiming to maximise beneficials. This is where we have all of the same as the second field, with the field margins at the edge, the cover cropping, but to this we add organic compost and we add the in-field strips that are programmed in using GPS as headlands within the field, so they're protected from nutrient drift, hopefully, and and pesticide drift. They're just dividing the field up into 3 strips, if you like. These are placed every 100 metres to overcome that 50-metre limitation on spillover. Okay, Barbara, thanks. I'm nearly finished. So this is what one of the infield strips looks like in the first year. The project has been running for the first year. It's cut multiple times in the first year to control annual grass weeds like blackgrass, but nevertheless, it's still producing some flowers. This is what it looks like from Google Earth. You can see the spacing which fits in with the tramline system every sort of 100 metres, or 96 in this case. Monitoring and data, we monitor a great number of parameters. This is our robotic Skyline greenhouse gas monitoring system in operation in one of the fields, but we monitor crop yield, soil nutrients and organic matter, soil microbes, pests, weeds, beneficials, you name it, we're measuring it on all of these fields. In terms of natural pest control, we're looking at the abundance and diversity of the beneficials using standard vacuum sampling pitfall traps. We're doing pest counts on the crops. We do autumn aphid predation rates because we're very interested in BYDV control using this system. The way we do this is we glue aphids to cards or plastic sheets. It's one way of controlling aphids. It's quite time consuming though, gluing them to cards. And then we return frequently to see how many of the aphids have been removed at different distances from the strips and the field edge. Similarly, we use a similar approach for slug predation. We actually make plasticine slugs, because slugs are great predators caribid beetles are great predators of slugs, so we make a little plasticine replica slug like this one, and believe it or not, we can count the bite marks in the plasticine, and that gives us an idea of the rate of predation. This was an earlier version of our slugs. A little bit too time-consuming and cute, though, to make those. Finally, my last slide, I just want to basically say that one of the aims of Assist is to ultimately come up with evidence-based practical guidance on how to improve IPM on commercial farms, in real-world systems. We've done this to a degree with our book on habitat creation and management for pollinators, but we're looking to take the same approach of this very practical guidance to support farmers and growers on how to improve IPM systems in their fields. So if anyone's interested in working with us, please get in touch. Thank you.